Welcome to our topic today, quality control of liquids, dosage forms, solutions and suspensions. From student of College of Pharmacy, Department of Pharmaceutics and AMP, Pharmaceutical Technology. Pharmaceutical Technology, the THU PPT 539. Topics for discussion 1. Principles behind the quality control testing of the raw in-process and AMP, finished products of the liquids dosage forms. 2. Full description of the tests used in quality control process of the liquids dosage forms. 3. Outlining and explaining acceptance limits and when batches are considered unsuitable for release. Principles behind the quality control testing of the raw, in-process, and AMP, finished products of the liquids dosage forms. Introduction to pharmaceutical quality control. This presentation examines the stringent measures that underpin the quality control of liquid dosage forms, particularly solutions and suspensions. It's an essential element in pharmaceutical manufacturing, ensuring that products meet the required standards for consumer safety and therapeutic efficacy. The importance of excipients in liquid formulations. In the realm of liquid dosage forms, excipients serve crucial functions beyond their role as inert carriers. They enhance the physical and chemical stability of the product, influence the bioavailability of the medication, and can affect patient compliance through taste and texture. Manufacturing considerations for liquid dosages. The production of liquid dosages is a multifaceted process that requires attention to detail in every step, from the solubilization of active ingredients to the final packaging. Ensuring uniformity, maintaining sterility, and preventing contamination are paramount throughout this process. Quality assurance, quality control tests. Raw materials. Quality assurance begins with the scrupulous testing of raw materials. It's a proactive approach to prevent issues in the final product. Every ingredient is evaluated for purity, potency, and compliance with pharmacopeal standards. In-process monitoring. The manufacturing process is continuous, with in-process controls providing real-time quality assessments. Parameters like pH, viscosity, and temperature are meticulously recorded to ensure consistency and quality at each stage of production. Final product. The culmination of the manufacturing process is the rigorous testing of the final product. Comprehensive tests are conducted to validate that each batch meets the predefined criteria for physical appearance, microbial content, and therapeutic efficacy before release. Stability studies in quality assurance. Stability studies are indispensable in determining the shelf life and storage conditions of liquid dosages. They simulate various environmental conditions to predict how the product will hold up over time, ensuring it remains safe and effective for the duration of its use. Regulatory compliance in pharmaceutical manufacturing. Adherence to regulatory guidelines is not just a legal mandate. It is a commitment to patient safety. Manufacturers must navigate complex regulations to ensure their products are consistently of high quality and manufactured to the standards set by health authorities. The role of documentation in quality control. Meticulous documentation underpins the entire quality control process. It provides a detailed history of each batch's production and testing, ensuring traceability and accountability. This documentation is vital for regulatory compliance and for internal audits. Conclusion: upholding quality standards. In conclusion, the principles of quality control in liquid dosage form manufacturing are the foundation upon which trust in pharmaceutical products is built. They ensure that every bottle, every dose, adheres to the highest standards of quality. Full description of the tests used in quality control process of the liquids dosage forms. Analytical methods. Validation. Validation of analytical methods is critical to ensure accurate and reliable results in finished product testing. This process confirms that the methods used are suitable for their intended purposes, upholding the integrity of pharmaceutical quality control. Testing protocols. Testing protocols are foundational in product testing, detailing every aspect of the process from the material's name and batch number to the analyst's identity. These protocols ensure that each test is fully documented for traceability and quality assurance. Stability testing for solutions and suspensions. Accelerated stability testing determines the shelf life under stress conditions like temperature and humidity. This includes sample collection in final packaging, initial testing for baseline quality attributes, and subsequent tests under accelerated conditions to monitor changes. Visual inspection. Visual inspection measures physical characteristics and appearance, including color, clarity, and container integrity. It is a critical quality control aspect, ensuring the product's visual attributes meet the established standards. Container compatibility testing. Container compatibility testing assesses the interaction between the product and packaging materials, ensuring the container system does not affect the product's quality, safety, or efficacy. Analytical equipment like HPLC assesses the product's stability and integrity in selected containers. pH measurement. The pH of solutions and suspension is measured to ensure stability and compatibility with intended use. A calibrated pH meter and electrode are used for this purpose, following specific steps for accurate pH measurement. Viscosity. Determination. Viscosity is measured to ensure the suspension's pourability and proper mixing. Viscometers, like Brookfield or Falling Ball types, are calibrated and used to assess the flow properties of the suspension. Particle size analysis. Particle size distribution is crucial for suspension uniformity and stability. Techniques like laser diffraction or microscopy are used following meticulous sample preparation and instrument calibration. Redispersibility testing. Redispersibility testing ensures suspended particles remain evenly distributed after shaking. This involves evaluating the suspension for homogeneity and particle distribution after a defined storage period. Microbiological testing. Microbiological testing detects harmful microorganisms, ensuring the product meets microbiological quality standards. Techniques like microbial culturing and PCR are employed, following strict sample collection and preparation guidelines, outlining and explaining acceptance limits and when batches are considered unsuitable for release. Understanding acceptance limits. Acceptance limits are defined criteria that a pharmaceutical suspension must satisfy to be deemed suitable for its intended use. They are established to ensure the safety, efficacy, and consistent quality of the suspension. Physical parameters for suspension acceptance. For pharmaceutical suspensions, acceptance limits include physical parameters such as the uniform appearance of the suspension, absence of large aggregates, appropriate viscosity and flow properties, the ability of the suspension to redisperse settled particles, and specific particle size distribution requirements. Chemical and microbiological criteria. Chemical parameters encompass pH maintenance within a specific range for stability, accurate concentration of the active ingredient, and minimal presence of impurities. Microbiological parameters set acceptable microbial counts, the absence of pathogens, and the effectiveness of preservatives. Establishing acceptance limits. Setting acceptance limits involves referencing pharmacopoeial standards and stability study data alongside a thorough risk assessment that considers the potential impact on patient safety to determine stricter limits for critical quality attributes. Testing and release of pharmaceutical suspensions. Batch release testing for suspensions includes sampling, analytical testing using validated methods against the set acceptance limits, and rigorous documentation of the results. Criteria for unsuitability of suspension. Batches of suspension may be deemed unsuitable for release if they exhibit out-of-specification results, physical instability such as caking or phase separation, exceed microbial limits, or show any deviations from the standard manufacturing process. Actions for handling unsuitable batches. For unsuitable batches, a root cause analysis is conducted to investigate the failure. Options include quarantining the batch, reprocessing to meet acceptance limits, destruction if reprocessing is not viable, and implementing corrective and preventive actions to avoid recurrence. The critical role of acceptance limits. The purpose of acceptance limits extends to ensuring patient safety by providing effective medications, compliance with regulatory requirements, and maintaining the pharmaceutical company's brand reputation through consistent product quality. Challenges in formulation and supply of suspensions. Challenges include formulation difficulties such as achieving uniform dispersion, preventing particle aggregation, ensuring redispersibility, and addressing the impact of storage conditions and global supply chain. Complexities on suspension quality. Thank you for listening. For more information and sources, scan the barcode.